Okay, we should be live. Pardon me while I manage some windows. Cool. Let's see. I'm going to start a new branch for this. This is kind of a new tangent. Okay. Okay, so here, get checkout branch. Evo. Okay, so let me talk about the goal here. So what we're going to do in this session, at least start to do, is implement an evolutionary algorithm on top of my ant colony. So first let me show you the ant colony so you know what we're working with. See, we run so var run app.py. Okay, so we have a traveling salesman problem with all these cities and all the possible paths between them. And now we send ants that go marching along. And we have this algorithm where basically the ant lays a pheromone proportional to the quality of its solution. So at first it's kind of just following this greedy heuristic, going to the closest city that it hasn't yet been to. And as we find cool solutions, it leaves more pheromone than when it has a bad solution. So what happens over time is we leave pheromones on paths that are good, because the other key here is that pheromone is continually evaporating. So as we lay down new stuff on good solutions and evaporate the bad solutions, then we have this emergence of a good set of candidate solutions that the ants can explore. So when an ant's making a decision of which city to go to, it considers both the pheromone levels and the proximity of the city. So if we run this forward, like right now, every path possible is equally probable. And you'll see it'll very quickly start trimming this down based on the greedy heuristic. And now it's kind of laying pheromone trails. And that's what we're visualizing here, is the strength of the pheromone trail, which will guide future ants. So this is our minimum distance found globally. So we run a bunch of iterations where we continually generate a solution, lay pheromone. That's one iteration. And here we're kind of keeping track of the best solution so far. And this is the best solution for each iteration. So what I'm hoping to do here is implement an evolutionary algorithm on top so that I can give different parameters to each of my ants and evolve that population over time. So right now I have alpha set at 1 and beta at 5. These are hyperparameters. But I think what we'll see is when we allow this to evolve over time, that we'll see some ants with one set of values and other ants with other sets of values. So we might have someone that specializes in exploring, whereas another ant specializes in exploiting good paths. That's the hope anyway. We'll see what happens. So the first kind of place to plug in here, actually let me give a link to this in case anybody wants to clone this code. And I will go ahead and put that in the description. All right, it should be saved. We'll cancel out of the app. Now, how are we going to do this? I don't actually know. I'm going to be figuring this out in real time. So I think our ants are going to stay the same, because when we create a new ant, we tell it which alpha and which beta. So at the time of creation, and these are the parameters I want to do evolution on. So at the time of creation, we'll pass in the values. So it's this model class that actually instantiates those. So if you look in our initialization method, we say for I in range number of agents, we create a new ant. We give it a unique ID, and we pass in the alpha and beta. So at this point, we could basically sample or do our evolution thing, right? So I'm thinking let's see, what are the concepts we need? Let's just sort of write those down in comments. I think we might actually make a different class here. Yes. I'm trying to think now, is there any reason I want to inherit from this class? I think not. We will have some duplicate code. It's kind of the boilerplate. But this will be completely different to initialize. We'll want to collect different data because we'll also want to collect things related to the parameters we're evolving. Update pheromone, I think, will be the same. That may be a reason to inherit. This will be almost the same, except we'll need to execute the evolution step. So one thing I could do is refactor this a bit so that I have like a, let's say, this code here is kind of looping through the agents and looking for the best distance. So that's like a data collection step. So I could separate this out as a method. And then I could have like a, let's say, I don't know, like a processing method or something, where in this case it'll just call this. But in the other case, we could call this along with like an evolve parameters method. So then we would still get kind of the benefits of some of this other code. So yeah, I think I will inherit and see what happens. So let's do this. Evo ant system. Evo ant TSP model. How about that? And then we will inherit from that. I'll go ahead and copy this. Normally I don't like copy paste because it's a sign that you should separate things out, but In this case, I already have separated it out, right? So when I call the initialization method on super, I'm going to have to pass in all of these things. So yes, exactly. Thank you, Copilot. But these won't make sense, right? Okay, so maybe I don't want to call this init. I want to call this init. So do I do super twice? Because this ant alpha and ant beta don't make sense anymore, since I'll be generating those from a distribution. Base of base class. I think you just call super twice. No, that doesn't work. How should I do that? Whoops. Oh, wait, I'm in the wrong place here. Okay, so I've made a bunch of mistakes. Let me unwind all this. I wasn't in the new class, I was in the old class. Okay. So I'll probably change this to like ant alpha mean. Because I'll really have 4 parameters. I'm going to have it like a Gaussian distribution for alpha and beta. So I'll need to specify the mean and the standard deviation. Let's see here. I guess I'll just Google how to call super of super in Python. Grandchild class. Okay, so we have grandparent, the child class method is hard coding the call. Crazy Costa. how to call init of and parent. Yes, this. Okay, this is like taking me down a rabbit hole that I don't know that I really want to go down to. They're all kind of saying the same thing, which is like doing this. Okay, I guess I'll just do this. So the grandparent class is this mesa.model. And I've already forgotten what the there's no arguments? Okay. I'm thinking, since I want to reuse so much of this, I could just create like a couple methods that do these specific things. Like, for example, initialize agents would be one, and initialize data collection would be another. And the rest I could just keep. I think I'm going to do that. So I will try to show you what I mean. Let's make sure, okay, we're in the original method here. So initialize agents, self. And now I'm just going to copy paste this. Okay, I thought I saved, yeah, TSP graph. So I can do self here. Okay, now I should be able to do initialize agents, ant alpha, ant beta. And initialize data collector. Yeah, I don't think I wanted to do all that. This I want to pull out. Okay, I can go ahead and do some type hints here. All right, I think this should be good. Now I should be able to just override these couple methods. But before I do that, let me test that I didn't break anything. Okay, looks good to me. Uh-oh. I've seen this before, but it's like a transient issue that I can't reproduce. It seems to be related to like when I make code changes arbitrarily. Okay. Reset. Cool. Seems to be working. No such com. Okay, we've refactored that. The thing I'm trying to figure out is what to do about this, because I can replace this function, but I still am passing in these kind of parameters that I won't be passing in the future. So one thing I could maybe do is create a dictionary of something called like agent parameters. I'm thinking something like this. Agent string float. I don't know if I want to be that prescriptive, but let's see. From typing, import dict. So then what I can do is agent parameters. So that'll expand this into alpha equals 1.0, beta equals 5.0 in the case of this default. The good thing is this can be very flexible. The bad thing is it's a little bit less readable. What might be better is to make this, it might be overkill, to make this a data class. Like a config data class, let's say. I'm trying to think about this. What I'm imagining is there's some base config class. And I could use that as the type hint here. That I don't know if it's, child A or child B. So instead I just specify the parent class. Let's say we call that config. We know it's some agent config object. And then here we'll use an static agent config. What was that? Static agent config. And then in the new class, we can use like a evo agent config, something like that. And the parameters will be different. How could I make this useful? Like a useful base class. Let's see what Copilot comes up with. I'm starting to think this is becoming overly complicated. But this is also kind of the fun part of writing code, in my opinion. It's coming up with the right abstractions. I think right now I'm making things overly complicated too early. So I'm going to keep what I have. And if and when things get confusing with this dictionary, then I will create some classes. Okay, so now we should be able to what is it? Agent parameters, okay. And then call super.init. What is it not like? Num agents, TSP graph. max steps, agent parameters. Okay, so now I can get rid of all of this, right? And instead change these two methods, initialize agents and initialize data collection. So the way I want to get started is a sample from a normal distribution. And I'll just use like unit variance. So I'll at least have some heterogeneity in my ants. Let's see. Does the built-in random Python random normal, does it have, or do you have to use NumPy? Okay, I'm not going to dig into that one right now. NumPy random normal. I'm guessing this is the variance. Yeah. Location and scale. Soon I will make those parameters also. I'm trying to think what data I should collect here. First of all, I want to put this here. Oops. Let me make sure. Okay, initialize agents. Alpha and beta. Okay, yeah, so that's what I want here. I guess I will duplicate this app. Because I have to change all the parameters and stuff. And I don't feel like generalizing it at this moment. I'm going to just get it to work. Okay. So now we no longer have ant alpha. We have ant alpha mean, I believe. Alpha mean and beta mean. And actually, we don't even have that, right? We have this outer dictionary, agent parameters. Agent parameters. A dictionary like this. Alpha mean, beta mean. And now instead of that model, we want Evo ant TSP model. Okay, let's see what sort of complaints we get. Float argument must be a string or a real number, not dict. Okay, so I'm obviously not passing in the right object here. So at where I sample this thing, okay, so I pass in the dictionary agent parameters, right? Agent parameters, it's a dictionary that goes from string to this thing, which will be a float. Initialize agents. Okay, I guess I'll do the old print debug. I guess it doesn't like that I'm wrapping we're nesting this thing. So I might have to undo that. We shall see. I don't think this is going to work. So yeah, it's not expecting that now. How can I do this? So the thing I'm trying to figure out is that I've abstracted this away so that I could pass in arbitrary things, which would be fine if I was just passing in the values. But since I'm using this like slider thing in Solara, it seems to not like this being nested. Like, if it's not in the outer level, it breaks. So I guess I need to refactor the code to erase this abstraction here, which is kind of annoying. It shouldn't be that picky. That's okay. I may as well rename this what it was, ant alpha, ant beta. Okay. Oh, this is really annoying though, because now I have to copy paste all this code. I didn't really want to do that. But hey, if it gets us running, we can figure out a better way to abstract this later. Okay. Alpha mean. I like being explicit with my arguments. Okay, this should work. Get rid of that. Yeah, let's see what happens. I need some plot that shows agent level information. Maybe I can just plot the sample average. Right now it should be close to this value, right? 1 and 5. But when we start evolving them, we should see it change. So let me implement that. So the model is going to keep track of okay, so what does the step do? All right, I want to make this a collect data method. And now I want to do the same thing as if I want to add this new stuff. Which, let's see, I can just call that. Agent.alpha, yes. And now I want to expose alpha means sample and beta means sample. Okay, so this should hover around 1 and this should hover around 5. Let's see what we get. Oh man, it's not reassigning. It's not updating the parameters of the ants. It's only doing it at initialization. I need like an update alpha, update beta for my ant. Hey, this is why we collect data, right? Okay, let's do that. So for our ant, I'm going to do this. I'm going to make this a property. This is the sort of thing that Copilot is great for. Whoops. Like, I would have definitely had to Google how to do that. And it's standard stuff. It's just, you don't do it all that often if you're someone like me. Okay, so what I just did, if you're not familiar with this syntax, so I did have self.alpha. I changed that to self.alpha underscore to be like this hidden thing. And actually, it would be better if I put the underscore in front. So let me go ahead and do that. Rename symbol. And the reason it's better to put it in front is because it will make it sort of a hidden attribute. You can get to it, but it's slightly hidden. Like, for example, if you're in a Jupyter notebook and you're doing like a tab complete, it's not going to list it in the beginning. You'll have to scroll all the way to the bottom. And it's sort of an unenforced standard that you don't change things manually that have an underscore that start them, a prepending underscore. And there should be some other way to access it, right? Because it's like an internal private variable or something. And now we have this official way of setting alpha. So we access alpha by calling, the class.alpha, just like we did before. And under the hood, it accesses this private variable or attribute. And then we use this setter method. So we'll be able to do ant.alpha equals value. And then under the hood, it will reassign our private thing to value. And same for beta. Okay. So that should be good. Now we just need to actually do the step. Okay, I'm going to remind myself. So just like I did with collect data, I'm going to call the step of my parent class, which has all the step logic. And then I'm also going to update the ant pheromones. Or sorry, update the alpha and beta parameters of my ants. Update ant params. Well, I'll call that agent params. Okay. So now it's going to loop through my agents, and then it's going to use my new setter methods for alpha and beta. And it's going to sample using my alpha mean and my beta mean. All right, this should give me what I want now. So we should see this bounce around instead of being static, but it should hover around 1.0 and this should hover around 5.0. Okay, it's always been greater than 5. That's odd. And likewise, this is like, has never been less than 1. But if I'm sampling from a normal distribution, it should be less just as often as it's... Okay, something's wrong here. One. Whoops. It must be doing like a cumulative, like it's not clearing this. Collect data. Is it something with the data collection? Like, is it not smart enough to do this property? Now, there's no way the alpha mean sample should be going up to 2.7. Okay, if you're just tuning in here, I have an ant colony with some parameters where each ant has these parameters that help determine how much it considers pheromone trails versus how much it just looks at the nearest city. And I want to evolve those parameters with time. And right now I'm trying to set it up so that each generation of ants samples from some distribution, those parameters. And once I have that going, then I can start adding in the intelligent evolution stuff of like, if you do good, then you have more offspring. And if you do poorly, then you die out. I haven't gotten there yet. I'm still just trying to sample from a distribution. And right now I'm sampling from a normal distribution with mean 1 and plotting what I'm getting. So it should hover around 1, but that's not what I'm seeing. So there's something wrong with my data collection. That's my thought anyway. What I'd like is an agent level visualization. Agent portrayal. Maybe that's what I need. Circle portrayal example. Oh, this is the network X graph. I could do something like I have a color bar that shows, for example, the value of alpha for each ant. Because what I'm skeptical of is that my data collection is broken and my values are actually correct. That's my hypothesis, because I don't know how I would be screwing this up. Alpha mean is 1.0. Oh, wait a second. Am I okay, that's the problem. I'm overriding this. That's what I'm using to sample from. Okay, this is just a stupid error. What do I call it? Alpha mean sample. So there's like the ground truth, and then there's the sample. And I was overriding the ground truth with the sample. Okay, now we should hover around 1 and 5. Do I not save that parameter? Okay. This is kind of ugly right now, but I think it's going to work. We can always make it prettier. Okay. Now, there we go. Now we're seeing it bounce around 1.0. And we are seeing this bounce around 5.0. That's what we would expect. I think this already is working better. Like I'm seeing much more drops to best solutions. And I don't even have any like reinforcement of good things. This is just like sampling the search space over time around something that's probably a good set of values. So just adding mutation is itself working better. That's really nice. Hey, K4. So I'm adding some evolutionary algorithms on top of my hyperparameters and doing a traveling salesman problem. So the previous iteration, every agent that was traversing the cities had the same parameters. Now I have it so that they're sampling from a distribution, and the next step is making it so that that my distribution itself is evolving, so that things that do well have more offsprings like it, and things that do poorly die out. So for example, let's say you get a value of, 1.5, and that does really well. But then some other agent gets a value of 0.8, and that does poorly. Well, then the next generation, I'll get more things like 1.5 than 0.8. And in that way, the population will converge on things that are useful. So that's the idea. But already I'm getting like much better results just by having the population vary its parameters. That's super encouraging. So once we start adding in the actual evolution piece, like right now, we're always sampling from a normal distribution with mean of 1, right? So it's going to like stay around here. And for the beta parameter, we're doing the same thing, but the mean is around 5. And we can set that mean with these sliders. But what we'll see after we add evolution is, let's say the actual optimal for alpha is 0.8. Then you'll see this sort of bounce around, but kind of slowly converge to 0.8. And likewise, if the optimal beta value is like 5.3, then you'll see this kind of climb up to 5.3. So that would be like the simplest case, is if there's a single optimum. But I think what the more interesting thing is, like, if the optimal value, because we have a bunch of ants all at once, right? So if the optimal is not just a single value, but like, 80% of them have 5.3 and 20% of them have 4.8. So then what you'd see is like a bifurcation, right? Where most things are up here, but then some things are down here. And we'll have like specialized agents where one is, for example, very sensitive to pheromones, and the other is not sensitive at all, and they kind of go off and explore on their own. I think that would be like the best case scenario result. So what we need to do now is add in that basic capability and also get the data collection. So if I think about that second case where like the optimal is a mix of a high thing and a low thing, if I just plot this average, then I won't see that, right? Because like if you average a large thing and a small thing, you just get a medium thing. But really what I would like to see is it like kind of split, where a lot of things go to the large thing and some of the things go to the small thing. So I need to think like, how could I capture that? I wonder if I made like a something like a fitness or an environment plot where you have like the alpha values. How would this work over time though? Maybe it's as simple as like a histogram of the alpha values and a histogram of the beta values. Because then we'll have like, in this case, we'll just have a bell curve around 5 for beta and around 1 for alpha. But if we got the sort of behavior that I predict we'll get, or hope that we'll get, you'll see that bell curve split into like 2 bimodal things where you have like 2 peaks, right, at different places. And one might be higher than the other. Oh, I don't know what's going on here. I think my camera's getting broken. Okay, I don't know if my stream is still working. Leave a comment if my cam stopped working. I heard some weird clicks. Okay, so I think the next step is to get the right visualizations, because the worst case scenario is I implement stuff and I don't know if it's working or not, right? Because then you can waste a lot of time. So I think data collection is key here. Okay, so let's do make histogram. Get agent vars data frame. So the ant, okay. Initialize data collection. So we have the model reporters, we have the agent reporters. So it's just called alpha, okay. Okay, we'll rename this to harm values, and we'll call this param name. What the hell is going on with the camera? All right, this thing is making like a clicking sound every couple seconds. Doesn't sound good. Here, give me just a second. I'll unplug it and plug it back in. Okay. Hopefully that works. Oh, make histogram. Float object. All right, what the hell are we doing now? Nan min. Okay, so yeah, we expect this to be like a bell curve, right? Centered at 1. And that's exactly what we see. But wait a second. Is this continually adding to it? Yes. So it's not the most recent step, which is what I really want to see. It's like cumulative. And I don't necessarily want that. Okay, I'm going to run this very temporarily. Yeah, 500 rows, 400 rows. Okay. So how do I get only the most recent step? Maybe I could do something like that. I mean, this... I'm not feeling too good about this, but let's see what happens. I don't know what the hell it's printing. It seems like the last row. But with a multi-level index. Oh, well, shit, wouldn't that be easy? And I don't have to mess with the data frame. Okay, let's see if that works. $12, $14, okay. The confusing part is that it's like always changing the y-axis. So I think it would make sense to set that statically. Let's see. Actually, I think that's a property of the model. Let's see. Num agents, right? Max.set ylim equals 0 to model.num agents. All right, let's see if this works. Okay. Let's do the same thing for beta. All right, this is really bugging me to copy paste this whole thing and just change one variable. Yeah, I can't in good conscience do this. I hate copy paste things like that. So I'm going to have to, let's see, get adder agent param name. Okay. The only pain in the ass is it's you're gonna have to do like a function thing here, because this assumes you call it with just the model, I guess, and I'm calling it with the model and the parameter name. That's okay, we can handle that. A function with default with func tools, partial. Yeah, okay. I always forget exactly what that's called. Func tools import partial. So now I think we can do partial. We want to call make histogram. Yes, that's exactly what we want. So now this should call the function, but use alpha, and it should call the same function with beta. So we should have separate things for alpha and beta now. Distance histogram. Okay, that's not what we want. Param name histogram. Okay, alpha histogram, beta histogram. All right, now let's see. It should bounce around, right? Cool. And I want my graph to come last. Okay. Cool. So now we have, I think, at least the core functionality to know what we're doing. We might be able to drop these because we should see just as much, if not more, information here. I guess the thing we get to keep here is the time history, right? Because this is just a single snapshot, and once you look at it, it's gone. It'd be really cool if we had like maybe bar, I don't know. Basically, I'm imagining this histogram turned on its side and plotted over time. That'll have to be for a future video. Let's keep this relatively simple and get the core stuff going. Man, I'm really impressed with how this improves over time. Because if I turn that off, here, let's just see what this value is. It's like what, 22,000, something like that. Let me open another terminal and run it the old way. Oh, come on. You can't use a different port? Well, I'm just guessing. Hey, it worked. Okay, so this has every ant with the exact same alpha and beta parameters. So this will set alpha equals 1, and this will set beta equals 5. So no sampling from a distribution. And you'll see that this sort of quickly stops improving, whereas this one seems to like have lots of improvements. So it's below 22,000. And you can see this is well above 22,000. And you also see like this average. So this is the best distance for each iteration. And you see it's kind of climbing up, right? It's like the ants are reinforcing a not so great solution and being increasingly pulled into that suboptimal solution. Because like ideally it would be pulled to whatever solution this is and like stay down here. But it's not. It's like going up to the suboptimal and it stops improving. Whereas here, it stayed down, and then it has these occasional big drops. That's very cool. So we're at 100 iterations, and we've seen like the first big drop and then one more drop. Here at 100, we'd seen like a bunch of drops. We've kind of stopped here. We might be at the actual optimal. Let me get the actual optimum for this. And I'll draw it as a line, and we'll see how close we can get to it. Man, where is it? TSP lib, documentation. No. Oh, best known solutions. Okay. So we are using, is it KROA 100? I think that's right. Data, KROA 100. 21,282. So let me, shit. I don't have any way to customize this graph. Okay. This is once again a little bit annoying, but I think it'll be useful. I want to see if this works, and if so, I'll add the right axis to it. Okay. I think so. X.H lines. What is it called? Step or something like that? Num steps. Where'd we go? Okay, so now we have our optimal here. But wait a minute, this is drawing best distance iter, and I want best distance. And I liked the blue that it had, not this over the top blue. There we go. Cool. So I'll replace that other graph with this one, and then we should be set. Cool. Now, I should copy paste that over to this other one for comparison. Let's see, where did we go? And we could take the quotes off, and it'll use that function. All right, we'll let this run while we keep coding. These look pretty similar right now, actually. So this is right above 22,000. We'll keep our eye on this as we keep implementing. Cool. All right, so what should we do next? I think we should get some evolution going. So we will not have to change how we initialize our agents. This should be the same. This is what we'll need to change. This should be good. We might need to add a new method here. So basically what we want to do is have this like reproduction step, right? So if we think about evolution, I'm going to comment this out. So we have survive, kill, reproduce, mutate. So I'm trying to think. There's going to be a million different ways to do this, right? And this is like the details of the algorithm. I want to do something simple. So maybe we take like the top, I don't know, let's say 10% or 20% most successful of the ants. And then we let's see, what should we do to their parameters? We don't want to copy them exactly, right? We want to add a perturbation. So maybe we have like a noise distribution that's essentially the evolutionary step size. So, for example, if we're talking about the mean of alpha or beta or whatever, we could imagine a noise distribution of mean 0 and some standard deviation 1, let's say. And you sample from that, and then you add that to the mean of your parent. So, let me write that down to be a bit more clear. If parent mean is, say, mean P, and child mean, yeah, that's exactly what I was trying to say. So we have this normal distribution that's centered at 0. So you can be positive or negative, and some standard deviation. In this case, we have it equal to 1. And we take a sample from that. So that is sampling a mutation size from some distribution. And whatever that number is, we add it to the mean. So if it's, let's say, positive 0.1, then we increase the mean a little bit. it's like your kid is a little bit taller than you, right? Or if it's a negative number, then they're a little bit shorter than you. And if taller is better, then like if your child is, if you're tall, you'll have more children, and then your taller children will have more children than your shorter children. And so on and so forth. So you could imagine like the population mean increasing over time through the generations. So I think what we should do is have something like the top 20, let's say you have a population of 100, the top 20 survive, and each one of them have 5 offspring, something like that. And each of those offspring generate new parameters based on something like this, by some noise added to each of theirs, and now they're the next generation. So let me know if you think I'm doing anything foolish or not explaining it well. But I think that makes sense. So we'll do something like self.select winners. Self.reproduce. Self.mutate. I think we should do reproduction and mutation at the same time. You could also imagine, I think in this case we'll do like each one that survives will have 5 offspring. But you could also imagine like the number of offspring is proportional to the quality of your solution. So the best gets the most offspring, the second best gets the second most offspring, and so on. We can make that a future improvement. Right now, we just want the very basics. And the very basics requires there to be winners and losers, where the winners have offspring and the losers die out. And then there's this mutation that's passed down. Heredity plus mutation. Okay. So let's go ahead and define these methods. Select winners. Num winners. Okay. Yeah, I'm going to I don't need to do. And select top num winners. Did I not save that? No, okay. Winning agents, okay. Reproduce and mutate. Okay, so we've selected our winners, right? We sorted our agents by the distance. So the smallest distance is the best agent. So we sort from lowest to highest, or from best to worst, in other words, and then we take the first number of winners that we specify. In this case, we'll make it like 20% of the number of agents. Self dot agents per winner equals there we go. So I want to make sure that the remainder when I do this division is 0. Agents per winner. So now each one of my winners will produce this number of offspring. Offspring per winner. Okay. Reproduce and mutate. No. Let's see here. Let's see. This unique ID is not going to work, because then they'll all just have the same ID. Let's see. Okay, so if this is 0, then we'll have, let's say, 1 through 5. And then when this is 1, that'll multiply by 5. That'll start with 0 again. Oh, but this will go 0 to 5 minus 1, right? Okay, I think that's right. Okay, I want to make a let's see. A noise. Yeah. Because I think this is going to be too big. All right, now I have an agent. Instead of creating a new agent, why don't I just modify Yeah, I mean, maybe I just use my index to select the agent and then update their alpha and beta parameters. Yes. Agent index. Wait, is this going to mess up? Oh, yeah. The thing I worry about is as I'm looping through, I almost need to delete all of the agents and add new ones. Because what I'm afraid of is I'm looping through, and then I'll change the agent's parameters, but then I'm using the parameters here. So if I update the wrong one, then I'm not doing what I'm intending to do. So let's see. Is there a way to delete an agent? So we have schedule.add agent. How can we delete an agent? Okay, base scheduler. Methods, add, remove. Okay. So I think I can just remove all the agents. So select winners. This should return a copy, right? So I should be able to remove all agents. Oh, is that a thing? Clear? No, I don't think that's an actual method. I think Copilot is lying to me. Okay. Create all agents and remove from schedule. Remove. Okay. Wow. So this should create all new agents, right? Let's check on what our results are here. Okay, so the original version basically has done no improvement since around iteration, I don't know, less than 10. Here we seem to be doing quite a bit better, continually improving, although pretty long gaps in between. I wish I had a good readout of what this value actually is. I mean, it looks a lot closer, but I don't know how to. I mean, this doesn't even get below 22,000, right? Whereas this is well below 22,000. But we should change this somewhere so that we have like a display of the actual number. Okay, anyway, we'll get back to that. So now what we need to do is update the parameters so that we pass in the number of winners and the noise standard deviation. These we might eventually drop, but for now we will wait. Okay. Num winners equals 5. Sorry. Num yes. And noise standard deviation, I'm going to make a slider. Excellent. All right, so we're going to start at point 1. All right, we'll probably get slice indices must be integers or none, or have an index method. Num winners. Oh, is it because it's a float? The node none is not in the graph. I have a feeling this is because I'm deleting the agents. Damn. That means instead of creating new ones, I'm going to have to update the old ones. Update agent params. All right, let me think through this. I want to make sure that sorted returns a copy instead of a reference. I think it does. Python sorted return copy or reference. A sorted copy of the given list. Okay. Let's see what happens. List index out of range. Agent index. Oh, that's because I'm removing. I meant to delete that. Okay. So let's see what happens. We were going to stay at 5. Now it looks like beta is increasing, right? What's alpha doing? Oh, look at that. It's becoming bimodal. Well, it was. Interesting. I'm surprised these things are staying kind of close to where they started. Maybe the variance is too high. We'll see where it settles. Right now it was going a little bit off the rails, but is maybe coming back down. All right, what if I really let this have like a high mutation rate? So that means the children values can be pretty far away from the parent values. Let's see what happens. We're seeing a lot more, I think, viable like a lot more options instead of narrowing in on a specific path. Wow, beta's gotten really big. It's gone from 5 up to, it's kind of going off the rails. Wow, this is pretty fascinating. Look, beta has really, it's like doubled. It's still climbing. Alpha staying. So to remind you, beta is the exponent on the 1 over distance heuristic. So the stronger this is, then the higher the preference to choose a nearby city and ignore the pheromones. And then this exponent is like how alpha is how strong to consider the pheromones. So at first it was kind of going down, now it's gone up. I guess these things can just each get really large and keep competing that way. It's like when one gets bigger, then the other one has to get bigger to keep up, and then it could just go off the rails. Oh wow, now alpha is plummeted. Okay, I think like the next steps, one is going to be verifying that what I implemented is correct, because I'm not 100% sure that this code is working as intended. So I want to verify that. But assuming the code is working correctly, the next step I think is collecting data with different amounts of noise and different starting points and seeing how these best distance curves. So like, do we get to better solutions faster, or do we find optimal solutions in some cases and not in others? And what do these populations look like? It's like for the best solutions that we find, what do these distributions look like? I think that'll be the kind of interesting question. So we should be able to run a bunch of these in batch and collect data and then analyze the results instead of doing this like interactive visualization thing. This is super cool. I think the noise standard deviation is too high right now because it's like having these wild swings, and we're not seeing much improvement through time. We also need to set, I think, the variance of these distributions as another parameter we evolve. I would like to do that before wrapping this video up, because I have a large variance right now of 1. Okay, so let's go ahead and do that. Yeah, I don't need to pass this in if I'm saving it, right? So let's get rid of that. Okay, so we initialize. We're not even calling this anymore, right? Yeah, we can delete this method. Wait a second. What am I doing here? I guess I only use the standard deviation on alpha. So in other words, this normal distribution only for initialization, right? Because when I reproduce or create a new ant from a parent, I just nudge it by this amount. I don't sample from another normal distribution. It just inherits. Yeah. Okay. So that means I don't need to do this. We can set this to whatever we want because it's only the very first generation. It shouldn't matter. Oh yeah, I think this is good. It's this guy that really matters. Because that's the one that determines the variance of the nudge. Okay. I think we're at a good stopping point. The only thing I really wish I had maybe, so I want to know how far away I am from the optimal. So maybe one thing I could draw is like the optimal minus this may give me the same problem, but I'm thinking about a plot that instead of getting the actual distance, it's like the distance minus the optimal. So it might scale the axes a little bit better. Let me try that real quick. If it looks good, I'll clean that up. So these ticks are like 500, right? I don't know how this is going to look as it scales. Okay. That's pretty good. All right, where do I want this thing? Maybe in place of that. And I'll do the same thing on this one. All right, let's see how this evolves in comparison to this one. Okay, we're sub 1,000. Okay, we've hit 1,000. Yeah, this might start to not look so good as we get, 1,000 steps or something. It's just the dots are too big. I'll have to put some thought into maybe one stupid thing I can do is just put it in the title. All right. It's like a hacky way, but it's sort of working. Interesting. Okay. So right in this iteration, it seems to be pretty sensitive to the initial conditions. But in this case, we're down to 730. Here we're at 885. So maybe I'll let this run for a bit and see how this evolves. No pun intended. Edward, yes. I put in the description of this stream where we started here. So I forked the Mesa examples. So if you go to ACO TSP in there, you will be able to run this version, which does not have the evolution stuff. But I will push this branch when I'm done with the stream. Or hell, maybe I'll just do it right now. Yeah, I might as well just do it. Let's see. What do we want to commit here? Yes. 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 Okay. Initial Evo implementation. Oh boy. What's it complaining about? Okay, so it's doing some linting. I'm okay with that one. Okay with that. What is it doing? It's adding new lines, okay. Okay, I gotta see why this is failing. So it has like this automatic code checker that runs. Found one error. Remove unused import typing.dict. Okay, I thought I did use that. Okay. Make sure I'm on the right branch. I'm going to push it to my fork. All right, cool. So you should be able to clone this repo and check out the zjost evo branch. And that has all the stuff in it. So there you go. What happened here? Why isn't this running? Yeah, I don't know why this stopped. Oh, okay, because I updated those files. Got it. Cool. So yeah, I think I'm going to stop for now and figure out what's the best way to make sure that this code is doing what I think it is. If it's a visualization or what. And then from there we can scale up our data collection and see what kind of interesting insights we can get. Cool. Thanks for anybody that tuned in. I'll see you guys soon.